Welcome back, everyone. We're here with more reinforced concrete, and today we'll learn about how to calculate the cracking moment of a beam. Let's start off with a recap of reinforced concrete beams in Flexure. So we have three stages. We'll have the uncracked stage, the cracked stage, and then the yielding stage until it reaches ultimate failure. Now in this video, I'm worried about the uncracked stage right here, and I want to find when that stage ends. And that will be at a moment called M sub CR, that's our cracking moment, and that's associated with a curvature CR, my cracking curvature. So let's get down to business. First, we're going to make the distinction between two theories or ways that we can approach this problem. So on the left here, I'm going to consider the gross section approximation, and then on the right, I'm going to consider the transformed section. And these are different in how I treat the steel in this pre-cracked stage. So in the gross approximation, I'm just going to totally ignore the fact that I have steel there, and I'm just going to look at a pure concrete section in bending, uncracked, so I get the entire cross-sectional area. Now this will give us a value I sub g for the moment of inertia, where the g is standing for gross. So oftentimes we'll call this I gross or the gross moment of inertia. On the other hand, if I have a transformed section, I need to transform my steel area by converting it into N by AS, where AS is the area of the steel, and then N is the ratio of my modulus, ES to EC. So effectively, this is converting my steel area to an equivalent concrete area, where ES is the modulus of my steel and EC is the modulus of my concrete. Now, usually to do this, we add little wings to the side of our section there at the layer of the steel. And because my total area is N times AS, and I already have one AS in here, we're going to be adding wings that have area N minus 1 times AS. Now, for this section, the calculations are a bit more complicated because I don't have just a rectangular section that I'm going to consider. I have this wing-shaped section, but we will do both in this video, and we're going to start off with the gross section. We're going to start with a quick derivation and discussion of some of the theory that we're going to use for the gross section area. So the first thing that we need to be able to calculate is our moment of inertia, and it's going to be the gross moment of inertia, I sub g. Now, in this case, I'm dealing with a rectangle, so that's pretty straightforward. I have I sub g for a rectangle is 1/12 base times height cubed, where the base dimension here, B, is the width of my concrete section, and then H is the total height of the section. Next, I need to know something about my concrete stress. And fortunately, this follows standard beam theory, where I can say that my stress is just equal to my moment times y over I. So here I have stress, and I'm going to represent stress with a F. That's traditional in the concrete literature, is equal to my applied moment M times y. That's the distance from the neutral axis to the point of interest in my section, divided by my moment of inertia, which is equal to IG in this case. Next, I want to check when this thing is going to crack. And we're going to crack when my stress F at the tension face is equal to something called FR, the modulus of rupture. Now, in this case, my tension face is down here at the bottom, so I want F at my tension face equals FR. And that modulus of rupture, if we look in ACI 318.19, in section specifically 19.231, we'll find that this is 7.5 times the square root of F prime C, where F prime C is my concrete strength in compression. One thing to note here, all the units have to be in PSI for this equation to work. And if you're using megapascals, there is a different expression because the unit conversion is a little bit weird for this particular equation. So we'll be doing this in PSI in this video. All right, so now we want to know what moment is going to cause a tensile stress equal to my modulus of rupture, F sub R. So we'll rearrange our concrete stress equation. We have F sub R is equal to my cracking moment, MCR, multiplied by YT. That's going to be the distance from my neutral axis down to that tension fiber. And then divide that by I gross. Rearranging that equation gives me M cracked is equal to FR times I gross divided by y sub t. Perfect. So now we have a cracking moment. And maybe I'm also interested in my curvature at the point of cracking. If I want to draw my moment curvature diagram, we can go ahead and do that. My curvature at cracking. This is just derived from the expression for linear beams that my moment is equal to E times I times my curvature. And in this case, the E is the modulus for my concrete, I is I gross, and then my curvature is, of course, the curvature at cracking. Rearrange that thing, and we get my curvature at cracking is the cracking moment divided by my modulus and my moment of inertia for the gross section here. So those are the two expressions that we'll be using, and we're going to do an example of this on a simple rectangular beam. So here's our beam. We have normal weight concrete, 5,000 PSI is my strength, and I'm using grade 60 steel with a 60 KSI yield strength. And I want to calculate the cracking moment and curvature at cracking for this particular section. Dimensions are shown here on the left. I have a 16-inch wide beam, it's 26 inches deep, and I have 3 number 9 bars. Of course, that doesn't really matter here because we're going to be doing a gross section for this first example. So I'm just going to cross out that steel. We don't need it. So to start off, I need a gross moment of inertia, and this was for a rectangular section 1/12 BH cubed. So plugging in the numbers for that, it is 1/12 times 16 inches wide times 26 inches high, and cube that. And this is 23435 inches to the fourth. Next, let's move on to find my modulus of rupture, FR, and this is 7.5 times the square root of F prime C if we're using units of PSI. So this is equal to, plugging my numbers, I have 7.5 multiplied by 5,000 PSI, square root of that, is equal to 530 PSI. So the result of this equation is always PSI, and the inputs to that equation are also always PSI. And again, if you're using megapascals, there is a separate expression for that. Next, I want to calculate my cracking moment. I actually have all the information that I need for that. So the cracking moment, again, is FR, modulus of rupture, multiplied by I gross, divided by Y sub T. So substituting in my numbers for that, FR, modulus of rupture, is 530 PSI. And I gross, I just calculated that above, so it's 23,435 inches to the fourth. And then I'm going to divide by YT. Now that is, in this case, the distance from your centroid down to your tension fiber. And because this is a symmetric section and I'm ignoring the steel, that's just half of the height. So this is 13 inches down. So I'll divide this by 13 inches. And calculating that out, that's 956,000 pound inches. Now, pound inches, not a particularly useful unit for moments. Let's convert that to kip feet because that's a little bit more convenient. So to do that, I'm going to multiply this by 1 foot divided by 12 inches. That cancels out my inch units. And then I also have 1 kip per 1,000 pounds. That's going to cancel out my pound units, and I'm left with kips and feet. And this is going to be 80 kip feet. Now that we have a cracking moment, let's go ahead and get a curvature. To do that, I'm going to need to know my modulus of the concrete, or the elastic modulus. So that's E sub C. And if we look in section 19.221, we can find that this is for normal weight concrete, 57,000 multiplied by F prime C. And again, everything in here has to be in terms of PSI. So if I plug those numbers in, 57,000 multiplied by the square root of 5,000 PSI gives me a modulus of 4,030,000 PSI. So 4,030,000 pounds per square inch. Lastly, I can get my curvature. So my curvature is going to be equal to my moment at cracking divided by E of the concrete and I gross. And I have all those numbers, so it's just a matter of plugging these values in. For my moment, I'm going to use my value in terms of pound inches because my modulus is in PSI and then my moment of inertia is in inches to the fourth. To make sure that everything is consistent, I'm only going to have pounds and inches, and then all my units will work out. So my moment, 956,000 pound inches, divided by my modulus, which is 4,030,000 PSI, and then my moment of inertia, which is 23,435 inches to the fourth. So when I calculate that out, it is 1.01 times 10 to the negative fifth, 1 per inch. So the unit may seem a little weird there, but that is the unit for curvature. It is a strain per inch depth through my section, or a strain per length here. And since strain is unitless, the units for this expression looks just like 1 over inches. All right, so that is our gross section. Because I promised it, but not because it's pretty, let's look at the transform section. Now, for looking at the transform section, as I mentioned previously, the first thing that we need to do is we need to transform our steel area. So we're going to add our little wings here at the same depth as the steel, and it's going to have an area combined between those two wings of n minus 1 times the area of steel, AS. And I'm going to be considering two areas in this section. We'll call this area A, and the wings are going to be area B, where area A has an area of B times H. So B, of course, is still the width of my section here, and then H is going to be the total depth. And then I need one other variable. I'm going to need this distance D right here, which is the distance down to the center of that steel. The first thing that I need to do is I need to find my centroid for my section. And that's a little bit harder because I can't just say it's halfway down, so half the distance H, because I have these two little extra wings attached to my section. So what we have to do for this is we have to say that the centroid X bar is effectively like a weighted average. So I'm going to take the summation of all the areas multiplied by the distance to those centroids for those areas, and I'm going to divide that by the total area. So in this case, I'm going to consider two separate areas. Area A is B times H right here, and then area B is going to be just the two wings on the sides. Next, once you have a centroid, then you can calculate your moment of inertia. Now, the moment of inertia here is going to be something called the transformed moment of inertia, I sub TR, and it will always be greater than I gross because I've added two wings to my section. To calculate this value, we're going to need to know the moment of inertia for a rectangle, which is 1/12 BH cubed. And we're also going to need to be able to transfer areas to a new centroid. So getting areas to a new centroid is equal to area multiplied by the distance squared that it's being transferred. Once we have our new moment of inertia, the rest actually works essentially the same. So if I need my cracking moment M sub CR, we're going to find that this uses the same expression that we had seen previously. My cracking moment is FR, which is the same. That's just a property of our concrete, multiplied by I transformed now divided by YT. And remember that YT is the distance from my centroid down to my tensile fiber, but my centroid has moved slightly since the gross case, so that's a different number. If I also want to calculate my curvature, I can do that too, and it is in fact the same exact expression. So I have my curvature at cracking is the cracking moment divided by the modulus of my concrete, and I transformed. So those two expressions are the same. I'm just going to be using a different moment of inertia, the transform moment of inertia. Now, this calculation is going to be a little bit more complicated, but it's also going to be more accurate. So if I want to get a very precise number, I can do this. However, in practice, most of the time, we're just going to stick with the gross one and call it good enough. That said, let's actually do this. So I have the same concrete section. I want to see what that difference is between my gross section and my transformed section. I already have my elastic modulus and modulus of rupture, and I'm also going to need the elastic modulus of my steel, which is always 29,000 KSI. So the first thing that I'm going to do is I'm going to get my ratio N, which is ES over EC. So N in this case is 29,000 KSI for the steel and 4,030 KSI for the concrete, and this ratio is 7.2, and that's unitless. Next, I want to find a transformed steel area, and that's n minus 1 times the area of steel. I have for my steel 3 number 9 bars. So a number 9 bar has a diameter of 9/8 of an inch. The number corresponds to the number of eighths of inch that the bar diameter is equal to. So I have 3 9/8 inch diameter bars. Turns out that those bars have pretty close to 1 square inch per bar. So in total, 3 of these gives me 3 square inches of steel. So to get my transformed area n minus 1 for my wings, I have 7.2 minus 1 multiplied by 3 square inches, and this is 18.6 inches squared. So if I draw down here my little transformed section, I'm going to have my rectangle, and then I'm also going to add my wings on the outside, and together those wings have 18.6 inches squared. And they're going to be at a depth in my section of 23.5 inches down from the top. Next, I want to calculate my centroid. So my centroid, x bar, this is equal to the sum of ai times the x bar I, so that's the centroids for each particular region I'm looking at, divided by my total area for my section. So if we calculate this out, of course, we have 2 regions. We have region A, this rectangle here, and then region B is my wings. So we'll consider both of them separately. And I'll have x bar is equal to the area of my big rectangle A is 16 by 26 inches. And then its centroid is 13 inches from the top. That's half the distance down. Plus I have an area of 18.6 square inches for my 2 wings, and that is a distance 23.5 inches from the top. And I'll divide this by my total area, which is 16 by 26 plus 18.6. And we'll find that the centroid is at 13.45 inches down from the top of my section. So if I sketch that out, it's right about here, and it'll be 13.45 inches down. Lastly, I want to calculate my I transformed. And I have 2 regions here that I need to add together. So this first line is going to represent my rectangle of my concrete. It has a moment of inertia of 1/12, 16 inches times 26 inches cubed. That is the moment of inertia for a rectangle. But then I need to transfer that area to my new centroid. So it's only being transferred 0.45 inches. So it's going to be transferred from here, for example, 13 inches down to the new centroid of 13.45 inches down. So we'll do that. That transformation is the area, which is 16 by 26. And then the distance is 13.45 minus 13. And that distance is squared when we're transforming this. Next, I have to consider my second part. That's B here. Now, generally, this looks like a rectangle as I've drawn it, but it's so thin that I'm just going to consider that H for that rectangle to be effectively 0. So I don't have that term. So we'll just have a 0 plus, and now I have an area, 18.6 square inches, that needs to be transferred to my centroid. So it's going to be transferred 23.5 inches minus 13.45 inches. And I'm going to square that to get over to my centroid. And I'm going to add all that together, and I have 2,5,396 inches to the 4th. So as we see, that is in fact a little bit bigger than my gross moment of inertia, which we've expected because I've now added steel to my section. Now that we have the transformed moment of inertia, we will go to the next page here and calculate the cracking moment and the cracking curvature. So to go ahead and do that, step 5 is my cracking moment. It's the same equation. It's FR, except I'm going to use I transformed on top, divided by YT. YT, again, if we draw our centroid here, which was 13.45 inches down from the top, YT is therefore going to be this distance right here from centroid down to my tension fiber. So that is going to be 12.55 inches out of my total 26-inch section. So putting some numbers to that, M cracking is going to be 530 PSI multiplied by my transform moment of inertia. That was 25396 inches to the fourth. We're going to divide this by the distance, 12.55 inches. And that is going to be a moment of 1,073,000 pound inches. Now, I want to convert that to kip feet because that's just a more convenient unit for moment diagrams and such. And I'm going to do this conversion in one step here. 1 kip foot is equal to 12,000 pound inches. So going through that is 89 kip feet. So lo and behold, by considering my steel, I increased my cracking moment by about 9 kip feet. So that's roughly a 10% increase, a little bit more than that. So not bad. And again, this is a more exact approximation, but you'll notice that the gross section was actually conservative. I had a slightly lower cracking moment, and that's more often what's used in design. Lastly, let's find our curvature. So again, the curvature is equal to the cracking moment divided by my modulus and my transformed moment of inertia. So let's put some numbers to this. My curvature is equal to 1,073,000 pound inches. Again, I want to make sure my units are consistent here. Divided by my modulus, which was 4,030,000 psi. And then my moment of inertia was 25396 while including my steel. And calculating this out, it is 1.05 times 10 to the negative fifth, 1 over inches. So again, that has also increased very slightly. So the gross section is the conservative or safe approximation when you're going through design. But if you need a more exact number, this will get you there. And that is how we calculate when a reinforced concrete beam will crack. We found the cracking moment and cracking curvature. This is, again, the linear stage in my concrete. In the next video, we'll transfer over to the cracked section, which is going to be a little bit different. So as always, I hope you learned something. Please subscribe, and I will see you next time.